Hey guys, hope everybody's doing okay. What we're going to do today is wrap up our thermodynamics unit with our last lecture of the unit here on free energy and equilibrium. Okay, so it's a pretty short lesson. Just want to help you derive an equation and do some practice problems using it. So on the screen here, this slide and the next one just helps me show you how to derive the equation that we're going to need. So just try to follow along to the best of your ability here, and then we'll really focus on what equation we're going to use and how to do some problems using that one. So under any conditions, standard or non-standard, the free energy change can be found with the equation on the screen. So sometimes we're not at standard conditions, and we need to find our free energy, and this is the equation that you would use. You really rarely, if ever, have to use this in the AP curriculum or on the College Board exam. So do not worry about committing this to memory or anything. But this is the equation that we would use if we're trying to solve for the free energy at non-standard conditions. We would need the free energy at standard conditions because of that little degree sign there, plus RT natural log of Q, which is the reaction quotient from equilibrium. All right. So under standard conditions, all concentrations are 1 molar. So Q would be equal to 1. Right, because Q is concentration of product over reactant, but if they're all 1 molar in standard conditions here, the Q term is going to be equal to 1, and the natural log of 1 is equal to 0. All right, so the last term drops out, and we end up with something else. So at equilibrium, Q is equal to K. We know that from our equilibrium unit, and we know from just the last lesson that at equilibrium, delta G is equal to 0. So what I want to do here is show you how Gibbs free energy is related to an equilibrium constant and how you can use one to find the other. All right, that's all we're talking about here. So you substitute a bunch of what we talked about into the equation, and we end up with 0 equals delta G at standard plus RT ln K, right? If we're saying we're at equilibrium here. So at equilibrium, delta G is 0. At equilibrium, Q is equal to K, so I plugged it in here. And let's rearrange it, and you get delta G at standard equals negative RT ln K. If you reorganize that to solve for your equilibrium constant, you have K equals E to the negative delta G over RT. These equations are what you need to know how to use. Okay? So don't worry about the derivation very much at all. Okay? Worry about how do I do the algebra with these equations and plug my numbers in. I think on the College Board equation sheet, you have this equation. I'm pretty sure you don't have this one. Okay, but some students like to memorize it because they have a hard time undoing a natural log. This is how that happens. All right, so you're either going to solve for delta G at standard or you're going to solve for K here. And you can see if I know one, I could figure out the other with some other stuff. R is your constant. We know what that is already. That's on your AP formula sheet too. 8.314 joules per mole Kelvin. All right. Of course, T is your temperature in Kelvin, and that's really about it. All right. So let's see how we use this. You have acetylene gas, C2H2, can be converted into ethane, C2H6, by a process known as hydrogenation. And the reaction is on the screen for you. It says, given the following data at standard conditions, so we have delta G at standard here, and all pressure equal to 1 atmosphere, 298 Kelvin, what is the value of Kp for this reaction? So I need to know what my equilibrium constant is for this reaction, Kp. It's Kp because everything's a gas in the chemical reaction. So normally to do this, to find Kp, I need the pressure of all components that are gases in this reaction. Well, I don't have any of that. Okay, but what I do have, though, is some delta G, Gibbs free energy, values at standard conditions. So what I could do is find the delta G at standard of this process, of this reaction. And the way we do that is just how we would find delta H or delta S if you're given a list of these values. So let's go ahead and knock it out here. So delta G for the reaction, that says reaction, equals the sum of the moles of your delta G at standard of your products minus the sum of the number of moles times your delta G at standard of your reactants, right? So this equation can be used for delta G, delta S, delta H. If you have all of your substances in your chemical reaction, to find the delta G of the reaction, you do what we have here. So that's going to be equal to, there's only one product, so there's 1 mole of it, so it's 1 times negative 32.89 from the table, and that is kilojoules per mole. All right, so kilojoules per mole. Minus, then we have 2 reactants, so let's make sure we do all this together here. We have C2H2, there's 1 of those, so 1 times C2H2, which is 209.2 kilojoules per mole, plus the, really plus 2 times the delta G for hydrogen gas, which is 0. That was easy. So plug it in your calculator, and you get a delta G for the reaction of negative 242.1 kilojoules. If you look at, now, keep that in mind a second, if you look at your equation that we had in the previous slide here, I want to find the equilibrium constant, which is K equals e to the negative delta G over RT. Look at your R value. You have joules there, okay? I cannot keep my answer here in kilojoules. So the units never going away, all right? So we gotta make sure we know how to do that. So you guys all do. So convert to joules here. And you get obviously 242,100. So 242,100 joules is what you end up with. Okay? So now you have K equals e to the negative delta G over RT. So what I do is I find, like, calculator mistakes happen all the time every year on this. So I type in my delta G over RT. Okay, I type that in my calculator. I hit equals. I multiply it by -1 because it's negative delta G over RT. And then I raise e to all that stuff. All right, so just to plug everything in for you, you have K equals e to the negative, forgot to carry the negative down here, negative delta G, so that's negative 242,100 joules over RT. So R is 8.314 joules per mole Kelvin times your temperature, which is 298 Kelvin. Okay, so do negative 242,100 over, and then make sure that you're dividing by 8.314 and 298, right? So you got to make sure in your calculator this goes in parentheses. Okay, it's just algebra. Okay, you don't want to divide by 8.314, then hit the times button, and your calculator is going to say, I'm going to multiply by 298. You're going to get a horrible answer. You want to divide by 8.314 times 298, that quantity. All right, and what you do if you type it into your calculator the right way, you should get an answer of something that's absolutely humongous, 2.74 times 10 to the 42nd. You're going to say, does this make any sense at all? And the answer to that should be absolutely, because look at your delta G value. It is extremely, hugely negative, right? That is extremely thermodynamically favorable, right? We want a delta G value that's negative for a spontaneous or thermodynamically favorable reaction. So this clearly is by a lot. You have negative 242,100 joules here. So that means it's extremely spontaneous. it works extremely well in the forward direction, right? So your equilibrium constant should be humongous. 2.74 times 10 to the 42nd is extremely product favored, forward reaction moving along, and that's what we have here. So both of these definitely check out in terms of like, do they make sense or not? Okay, here's the last one. It's just going through another little setup like this to figure out ultimately an equilibrium constant. So we have N2 plus O2 yields 2NO. And I want to use the following thermodynamic data to determine at what temperature in Kelvin the above reaction is spontaneous. Okay, so this is, means not really new, but it's a way to approach this problem here. I know the reaction is spontaneous when my delta G value is 0. Or I'm not 0, when it's negative, right? Wrong way. So I want to know when this reaction is spontaneous. So that's when I have a negative delta G value. Well, what you could do is think about like I want to find the exact place it's spontaneous. Okay, so it's really at like negative 0.0000001. Okay, if my delta G value is negative 0.0000001, it's a spontaneous reaction. Well, it's stupid to put that there, right? So what I could just do, if I want to find out when my reaction is spontaneous, I can just set my delta G value equal to 0. So I know if I go like, 9 decimal places or 8 decimal places over, it's still basically just the number 0. So I want to have delta G equals delta H minus T delta S and set delta G equal to 0. Okay, so now I plug everything in, I solve for T, and I'm good to go. So take a second, plug in the data on the screen, solve for T, we'll see what we get. All right, so if you plug everything in, you get delta H 180.5 kilojoules per mole minus T, which is what we're solving for, delta S, which is 24.80 joules per mole Kelvin. As soon as you see this, you're like, wait a minute, I got to stop a second. I can't have a kilojoule and a joule in the same problem, so I need to go ahead and change one or the other one. All right, so I always end up changing delta S usually, and what you'll end up doing is changing your delta S of 24.80 joules into kilojoules. So to convert that, you just do a simple factor label problem, and you're going to get 0.0248. 0.0248 kilojoules per mole Kelvin. Okay? If you do algebra the right way, you reorganize this, bring your delta S over, bring your, do your negative, because it's a minus T delta S is what you have left. You're going to get a temperature of 7,278 Kelvin. That's when the above reaction is spontaneous. Okay, so quite the temperature to be a spontaneous reaction here. So not going to happen at some of the lower temperatures, obviously, but that's how you solve it. So if you want to know when a reaction is spontaneous, you can set delta G equal to 0, because you know it would be spontaneous at like the smallest negative value you could find, which with sig figs taken into account is basically 0. Then just solve for T, and you're good to go. So we did something like this actually a little bit earlier in the previous lesson on the third law of thermodynamics and Gibbs free energy. Continuing on through that problem, says using the data below, calculate the Gibbs free energy for the reaction. So it's the same delta H and delta S value. I want to find out what the delta G on your note sheet. It has the Gibbs free energy delta G at standard conditions. Okay, you have to remember what is standard. Like, what are the standard conditions? Standard conditions are 25 degrees Celsius, which is 298 Kelvin. Okay, so all you have to do here is set up your delta G equation. We have our temperature this time, because I don't care. Like, this question said, when's it spontaneous? I didn't know what the temperature was when it was spontaneous. Here, I know what my temperature is. I know my delta H. I know my delta S. I need to figure out what my delta G is going to be. All right, so let's set it up. Delta G is delta H minus T delta S. We have the delta H, the T, we have the delta S. Just make sure you pay attention to your units again. They're the same numbers as the last problem. Go ahead and solve it, and we'll see if we're right or not. Okay, guys, if you plug in everything and you make sure you have your delta S value in kilojoules per mole Kelvin, or if you have your delta H in joules per mole, you could convert the 180.5 into joules if you wanted to. Type it in your calculator the right way, you're going to get 173 kilojoules per mole, or if you decide to go the route with joules instead of kilojoules, 1.73 times 10 to the 5th joules per mole. Notice your unit is kilojoules per mole or joules per mole. That's important. It's not hard to figure out. If you just look at if you include your units in your work, like I'm always harping on you to do, you have Kelvin here and here that cancel, and you have 180.5 kilojoules per mole minus some number in kilojoules per mole. Your unit is kilojoules per mole. All right. So please be really careful with the units and include them, because delta G is supposed to have, and it's that standard, delta G is supposed to have a specific unit on it, kilojoules per mole or joules per mole. Okay, so now that we have our delta G at standard, our delta G with that little degree sign, we want to find out what the equilibrium constant is for that reaction. So we use our equation, K equals E to the negative delta G at standard over RT. All right, so we have our delta G at standard. We just solved it on the last problem. We have our temperature, 298 Kelvin. We have our R value. That's on our formula sheet from the College Board, or I had it on a couple slides ago. So let's see if we can use our calculator the right way and figure out what the equilibrium constant is for this reaction. The delta G value at standard is 173. It's positive. And remember, positive delta G value means non-spontaneous. So when we solve for our equilibrium constant, that should coincide with what we're seeing there for our trend with that delta G value. Okay, if you plug everything in, now please pay attention to your delta G at standard value. It has to be the joules per mole version of it, because your 8.314 joules per mole Kelvin, your R value has joules in it. So again, we have joules here and joules here. So they will cancel. Joules and joules cancel out. Kelvin and Kelvin cancel out. All right, and so does moles and moles. So that makes sense. Our equilibrium constants never have a unit on them, right? We knew that all the way back from our 2 units on equilibrium that we've studied. So you plug it in your calculator the right way. This is E raised to all of this stuff here. I'm just trying to write it out for you so you can see everything. You're going to get 4.73 times 10 to the negative 31st. Okay? Makes perfect sense. Your delta G at standard is positive. That is not spontaneous in the forward direction. So that means very, 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 very reactant favored. Well, guess what? Look at your K value. 4.73 times 10 to the negative 31st. That's extremely reactant favored, right? It's a super small K value. So let's do one more. Determine the equilibrium constant for the same reaction, but instead of 298 Kelvin, we're at 2,400 Kelvin, which is the combustion chamber for an automobile. So that's where this reaction actually occurs. So that's why it's kind of a real-life example here for this. And it gives you the delta G standard for the reaction at these conditions is 1.22 times 10 to the 5th joules per mole. So they had to tell you the delta G for these conditions, all right? So you get 1.22 times 10 to the 5th. That's your delta G value. Plug that into your equation and see what you end up with for K, all right? So again, K equals E to the negative delta G over RT. Plug it in, and we'll see what we get. Okay, plug everything in. Again, 1.22 times 10 to the 5th joules per mole. over quantity. Okay, it's negative 1.22 times 10 to the fifth joules per mole over the quantity 8.314 joules per mole Kelvin times 2400 Kelvin. You see your joules cancel, moles cancel, kelvins cancel. And what you end up with is a slightly more favorable process, although still not all that great. 2.21 times 10 to the negative third. You can't see the negative there. It's there, trust me. Okay. It's still reactant favored, but it's not as reactant favored. So that's why in the combustion chamber for an automobile, 2,400 Kelvin is that temperature. You're going to create more product in this chemical reaction if we go all the way back to it. You're going to create more of this in the combustion chamber of the automobile than you are at room temperature, right? So that's not really going to happen much at room temperature. We saw our K value was to the negative 31st power. But that's why in a car, you're going to produce more of that NO gas, which is bad for the environment, and it creates acid rain. You're going to get more of that NO gas because it's a little bit more favorable to create a little bit more product than when you're at room temperature, when you have that really low equilibrium constant value. All right, so just a practical application of what we're doing here. It's really just algebra and knowing how to keep track of your units, like I talked about before, and use your calculator appropriately. All right, that takes care of the unit. We'll do a lot more practice and review, and if you need anything, just let me know. That's about it for today, though, guys. Thanks.